Hello. Welcome to the California Colloquium on Water lecture series. Thank you so much for coming. This is the last lecture of the semester, and my name is Linda Vita, and I'm the director of the Water Resources Center, and we're the main sponsor of this lecture series. But I also want to acknowledge the Colloquium committee that of faculty here on the Berkeley campus that are so responsible for the speakers that we invite to talk about water. And that's Professor Michael Hanneman, David Sedlak, Nara Simon, Joe Sachs, and Matt Condolf. So they really are the ones who help invite the speakers and select the speakers, et cetera. So I really want to thank them. I think we've had such an outstanding series of speakers especially this spring semester. And I also want to acknowledge our sponsors, because without the financial support, we wouldn't be able to put the series on and videotape them and pay for travel for some of the speakers and some of the other costs associated. So I want to thank the deans of the Colleges of Engineering and Natural Resources, the California Center for Environmental Law and Policy, that's at the law school, the Beatrix Farron Fund of the Department of Landscape Architecture and Environmental Planning, the Executive Vice Chancellor and Provost of the campus, and also the Berkeley Water Center, the Earth Sciences Division of Lawrence Berkeley Lab, and the Groundwater Resources Association of California. So I want to acknowledge them. And then just a few more quick announcements. If you are not now receiving a reminder email, we have a list that you can sign up on outside. We also have some brochures and other things, other information about the Water Resources Center archives. And I think that's it. And with that, I'll introduce Professor Nara Simon, and he's going to introduce our speaker for the evening.
The US Geological Survey is a remarkable organization. It was started some 130 years ago. And in its early history, water played a very dominant role in the creation of the survey. And right from the very beginning, starting from about the 1880s, 1890s, somehow the people who got involved with water developed a very scholastic tradition of not only doing observations themselves. Some of them were remarkably well-known, outstanding geologists and earth scientists. They also started a tradition of making their knowledge publicly available for all over the world. This has gone on for more than a century. Unless you are closely have followed, especially the groundwater branch of the United States Geological Survey and their water supply papers and professional papers and bulletins and so forth, and sit back and think about it. After 100 years, you suddenly realize what a body of work and what a contribution to human knowledge, apart from what they did for groundwater as a science and development of groundwater for society. In the process, they also developed an outstanding body of exceptionally competent scientists. They simply called themselves research hydrologists. They didn't give themselves much more fancy titles. And the US Geological Survey did not advertise them very much. But for anybody who has been in the profession of groundwater hydrology will know what contributions have come out of that organization over the past 100 years. And today's speaker, we have Dr. Leonard Konikow, who has been with the USGS for almost 40 years, 37 or 38 years. From the days of his graduate student at Penn State, he has been there continuously. And he had made very sustained, very basic, very important contributions in groundwater modeling contaminant hydrology, and more recently on groundwater basins. In fact, 2 years ago, he and another of his colleagues wrote a paper in Water Resources Research about groundwater depletion in the Dakota sandstones and in the East Coast Atlantic coastal plains. Suddenly I realized that USGS had 100 years worth of real observational data about groundwater depletion, permanent loss of groundwater from storage. The type of data which we don't probably get from anywhere else in the world. And groundwater depletion from storage is one of the most serious problems that is facing us today. And in the next 100 or 200 years, most of the big artesian basins in the world will run out of water if you are not careful. So today's talk is going to talk about the American experience, first-hand American experience about depletion of groundwater in the United States, and to reflect on the implications of that in a global sense, which is very, very important. And so it is my pleasure to introduce Leonard Konikow to exchange his thoughts today. Lenny.
Thank you very much, Nari. It's an honor and privilege to be here, and I very much appreciate Nari's invitation to come and present this talk. So thank you very much for the invitation and for your very kind words during your introduction. It's not very often that you see the words groundwater and global in the same sentence or same title. So groundwater is more often thought of on a local to regional basis. So I'm going to do that, but I'm also going to try to bring in a bit of a global perspective. And if we look globally, what we see, and I think you'll agree, is that we live on a water planet, a very, very wet planet, lots and lots of water. And of course, from space, you could really get that kind of perspective. And with all that water, it's kind of ironic, in a sense, that we deal with a situation that today, more than 1 billion people lack ready access to safe, fresh drinking water. And more than 2.5 billion people lack access to improved sanitation, leading to very serious disease, particular childhood diseases and deaths. And this number of 1 billion people, that's going to increase in the future. And this is something that is just astounding in this day and age that we have that kind of statistic in this planet that's so ripe with water. So what's the solution to this? Well, obviously it's more than a technical problem or a technological problem. There are many issues, but in the solutions, I'd like to think that groundwater is the path to a solution and a way to help solve this problem. And if we look at a world water budget, what we see and what I'll focus on is groundwater, and it's clearly, of all the water on our planet, it is the second most abundant volume of fresh water that we have, the most abundant being frozen and not that accessible to meet our needs for water supply. So with this vast resource of water, we could look at using groundwater, and in the United States in particular, groundwater supplies about 50% of the water supply in the nation. So it is a major component. It is our hidden resource. And among the public, most people are just not aware of groundwater, and it's something they just don't think about unless they happen to live on a farm or a rural area where they have their own well. And even then, they just don't know that much about it. So we have 50% of our water supply coming from wells. And where is all this water coming from? Well, again, to most people, it's a mystery, but to us as groundwater scientists and hydrogeologists, we kind of know the answer. Certainly, C.V. Tice's classic paper in 1940 laid out very clearly that any water withdrawn through wells, the pumpage, must be balanced by some combination of removing water from storage in the system, and that's what I refer to as groundwater depletion, removing water from storage from the subsurface. And in addition to balancing the withdrawals due to pumpage from wells by reduction in storage, there's some combination in addition of a decrease in discharge to the system as well as an increase in recharge. So some combination of these three factors always must balance the pumpage. So in this sense, it's very simple and easy to understand. But again, the more you look at it, there are some intricacies to this. If we take a system, a kind of a stream aquifer system, in the initial pre-development equilibrium, the discharge to the stream balances the recharge to the system. And when we start pumping, initially, 100% of the water withdrawn from that well is balanced by a reduction in storage. But particularly in a humid climate with recharge, that percent or fraction of the water removed from storage as a contributor to the pumpage will decrease with time, and over time, the amount captured from stream discharge will increase. So at early times, very early, it's all from storage. Then there's less water as the gradients change, less water discharging to the stream. And over time, as the drawdown in the well increases, you can actually induce infiltration from the stream. So not only is there less discharge, but you've increased recharge to the system by actually reversing the flow in the stream or in the aquifer close to the stream near the well. So these fractions will switch over time. When you get to a new equilibrium condition, all the water derived from the well is balanced by stream flow capture in this example, and there's no more reduction in storage. Now, depletion leads to problems, and we'll talk about some of these in a minute, but C.V. Tice's paper in 1940 expressed it quantitatively a little more, but these principles were known. Mendenhall, and this was a paper actually pointed out to me by Nary, he very clearly articulated, maybe in a more qualitative sense, some of the issues, and pointing out that, in a sense, you don't see this too much in technical papers anymore, but a clear recommendation: the man who wastes or uses needlessly a product on whose abundance the prosperity of the section depends is his own and his neighbor's worst enemy. Okay? And he was talking about, this was from a study actually in Southern California. 100 years ago, this was 1909. So the basic principles were known for a very long time. So some of the possible local and regional effects of groundwater contamination, of course, lowering the water table or the potentiometric head increases the lift, increases the cost of pumping water out of the ground, reduces the well yields. You could have environmental effects, land subsidence, degradation of groundwater quality, just a number of really detrimental effects. But one of the things that it leads to ultimately is a lack of sustainable development. Groundwater depletion is most typically typified by a decline in water levels. Here's just one example from the Las Vegas area where we had many tens of feet of decline over a period of several decades. One of the things that we're seeing in many areas, not in Las Vegas, is a kind of stabilization and slight reversal of these trends over the last decade or two. And it happens for different reasons in different areas, but there is definitely a common factor there in many areas. When we have declines in water level, sometimes it raises a lot of concern. We see lots of headlines in papers. This particular case is from the Denver Basin. an area south of the city of Denver where artesian aquifers are being pumped extensively and water levels are being drawn down so much that many wells have lost their ability to produce water. And this gets a lot of people very concerned and, of course, gets politicians involved in the situation. Interestingly enough, some of the cases, there's really the actual volume of depletion is really not that great. And we'll give you some other examples of this in a minute. In terms of environmental effects, groundwater depletion can affect stream flow, and it's not just in the US. This is an example from the North China Plain, and this is an area that's undergone very, very extensive, heavy development, drilling many, many thousands of wells over the last 2 to 3 decades. Okay, and what we see in this area, this is a fairly small river, but if we look at the mean annual flow, we see a definite trend here that correlates fairly well with the decline in the water table. In some years, after significant development has started, the annual flow is pretty close to 0 in some of these years. And this is the mean annual flow. So very serious environmental effects. We could see this also near Tucson, Arizona, where changes in vegetation, and this is essentially the same picture in 1942 and 1989, is attributed to declines in the water table on the order of 100 feet or more in this area. Land subsidence is a significant problem, very well documented in California with this very rather famous picture with Joe Poland. And this is a shot, I believe, in Arizona. But there are many areas around the US where land subsidence is directly attributable to groundwater withdrawals. Now, these are some of the local and regional effects. Are there any possible global effects of groundwater depletion? And I'll argue in a little while that groundwater depletion may be large enough that it may actually be contributing to sea level rise. There may be some other effects, and I think we'll have a couple of minutes at the end to speculate about some of those. Now, I'm not the first one to suggest that groundwater depletion may contribute to sea level rise. There was a paper, as one example, a paper in 1994 by Sahagian and Frank Schwartz and another colleague published in Nature, and it generated a lot of criticism. One of the main concerns, and a legitimate one, was that he didn't have the numbers, except for the High Plains Ogallala Aquifer system. There was really no numbers, no data. How much depletion was there? Okay, and it was hard to defend against that criticism because they didn't have the numbers. So about this time, one of the things I decided to do was to try to get the numbers, I naively thought I could do a global accounting, but that was just not possible. Now I'm trying to finish up a national assessment, and I think I've got a good handle on that. And as difficult as it was to do that in the US and get the data in the US, it's orders of magnitude more difficult to get that data outside the US. So we're going to start, in today's discussion, we'll focus on the US assessment. So in the US, where is groundwater depletion significant? Here's a map from a recent USGS study showing areas where water level declines have been greater than 40 feet since pre-development time. And pre-development time varies, but in most areas we're talking about the late 1800s through sometime in the 1950s as pre-development conditions. And you could see very extensive areas. The blue colors represent not areas, but rather wells that have reported groundwater declines greater than 40 feet. And it's pervasive. And some of these areas, I mean, we're talking about some almost the entire Atlantic coastal plain, big areas in the upper Midwest and so on, and of course, California and some of the desert basins. I'm going to talk briefly about the deep Cambro Ordovician carbonate aquifer system near Chicago, Illinois, in this area, just as one example. And then we'll contrast it with the Ogallala aquifer covering a larger area in the Great Plains. One of the differences, this is an artesian system, this is an unconfined system. So if we look at the Cambria-Ordovician aquifer system, we look at a record starting back in 1864, and in this case just through 1980, although this plot has been updated. But the map shows extensive cone of depression developed as of 1980. Okay, that's the change in head from pre-development conditions. Very, very large cone of depression with drawdowns exceeding 800 feet. Okay, that means the water level in the wells have gone down more than 800 feet in some of these areas. And what we see here is that since 1980, there's been actually a substantial recovery of heads of water levels. And this is attributable primarily to a shift in water supply sources, going more to surface water and shutting down some of the wells. Interestingly, the total depletion associated with this very large cone of depression is only on the order of 2 cubic kilometers of water. Not to say that 2 cubic kilometers of water is a small amount, but considering the magnitude of this, maybe it's not that great. One of the trends we could look at in terms of total freshwater use within the US that may be responsible for the pattern of recovery in the late 80s and through 90s is the fact that the total water use in the United States has stabilized certainly since 1985. Okay, population growth continues, but somehow water use peaked in the mid-80s and then has been fairly stable. And I think that's showing up in water withdrawn from aquifers and the water levels. We could see similar trend in the High Plains aquifer, also known as the Ogallala aquifer, where total groundwater pumpage from this system, and this again is a system covering parts of many states, kind of peaked around in the late 1970s to early 1980s, and then has been fairly stable in total, although variations between states certainly occur. Now, in this system, we have a water table or unconfined aquifer system. So when the water levels go down, that reflects a decline in the water table itself and represents and is coincident with a decrease in the saturated thickness of the system. And if we look at part of the 3 sample areas from Kansas to Nebraska to Texas, what we see, well, we should go Nebraska as being the northernmost. There's some declines up here, but most of the initial saturated thickness remains. A little further south as we go to Kansas, a little more serious, maybe 30% of the saturated thickness is gone. And then in the high plains of Texas, we've actually dewatered more than half the saturated thickness of the aquifer. Okay? And that's essentially non-recoverable on ordinary time frames. That is, we could legitimately call this groundwater mining. So if we look at the High Plains system in terms of the drawdowns, we see that indeed it's most serious in the southern High Plains where there are water level declines exceeding 150 feet in places, whereas in Nebraska, there's actually some areas where the water levels have risen since pre-development time. Nebraska is really sitting on an enormous volume of fresh water. They have a tremendous resource up there. Part of the rises are due to imported water diverted from surface water sources. So remember in the Cambria-Ordovician aquifer, we had about 2 cubic kilometers of groundwater depletion. The High Plains is the single most well-studied system in the US. It is the best documented case of groundwater depletion. Because it's so serious, they've put a lot of money into tracking water levels and accounting for everything. So they've done it over the years, and they continue to do a very major accounting. Through the year 2003 into 2004, there's been a total depletion, a net depletion from this system of on the order of 290 cubic kilometers of water. 2 orders of magnitude more than in the Cambria-Ordovician aquifer. So why is this? One, if you compare and contrast the two, one, this is a larger area. Second, it's an unconfined system. So for a unit decline in head, you're draining maybe 20% of that volume of water. Whereas in a confined system, a deep artesian carbonate system, your storage coefficient is probably 10 to the minus 4 or 10 to the minus 5. So a unit decline in head yields very little water, which is why the declines in heads are so much larger than in this system, and that the total depletion is so much less. Nevertheless, both of them represent serious problems. What's really a little surprising to me is that the depletion, the rate of depletion in the High Plains aquifer has not stabilized. Even though there's some stabilization of the total withdrawals, if you look at the data in terms of this is cumulative depletion, in the last few years, it's actually accelerated. And so a major concern here in the High Plains aquifer is that this is not showing, not yet anyway, showing any kind of slowdown in the rate of increase in depletion. Now, in some areas, depletion is recoverable. In some areas, particularly, well, as you would guess, areas with high rainfall and high recharge, the depletion, the drawdown can recover in some cases rather quickly. So here's a case in Brooklyn, part of New York City on the western end of Long Island. In the early 1900s, late 1800s to early 1900s, relied primarily on groundwater for water supply and for industrial use. And by 1936 had developed a very extensive cone of depression. This was about the time that New York City they expanded their water supply system and they brought in surface water to supply Brooklyn and Queens. And most of the groundwater pumpage stopped in the 1930s and 1940s, except for some industrial uses. And water levels recovered. So by 1965, there had been significant recovery. The interesting thing here is that during the 1920s, 30s, into the 40s, while the water levels, and again, this was an unconfined system, were low because of the drawdown, they built subways, high-rise buildings with deep basements, sub-basements, and now water levels are recovering, and they've got a lot of water to deal with in these subway tunnels. Okay, so it's an interesting problem that the temporary depletion kind of played a trick on them. So in trying to develop a national or global assessment of the magnitude of groundwater depletion, we face a problem that on individual systems this simply is not often done. In the High Plains aquifer is one exception. But in the rest of the US and around the world, no one's getting these numbers. And one reason, just people don't want to, it's not a question that they're used to dealing with. And so the data needed to get this are sparse. And in the rest of the world, again, in my experience with the US Geological Survey, when we collect data, it's out there for anyone to use or get or obtain at no cost. That's not the case in most of the rest of the world. You have the British Geological Survey, for example, collects groundwater data, and if you want to look at it, they'll be happy if you pay them. They'll let you share. They'll share the data with you if you pay for it. And in other parts of the world, they won't even let you look at it. It's considered state secrets. So anyway, it's an issue. So how do we estimate groundwater depletion? Okay, and there's a number of ways that you could do. In the High Plains, I simply integrated the volume of drawdown times a specific yield and came up with an estimate that way. One of the issues is how much depletion there is or drainage out of confining layers adjacent to confined aquifers. And this is another thing that we thought was very rarely done. Okay, and so we wanted to look at this. So Chris Newzell and I developed a method to make a first cut approximation of depletion from confining layers with the types of data that are commonly available. In detail, if we look at the hydraulics and everything, we know how to do this. We know how to estimate depletion. Okay, but the problem is, getting the properties of the low permeability confining layers is very difficult. There's very few measurements available, very few data available. And to do it rigorously, you need measurements of delta H, the drawdown in the confining layer, low permeability material itself. And no one wants to drill a well just to measure water level changes in a low permeability layer. That's not the focus of the people who are supplying water. So that kind of data is rare. So we need a method to do something else. So we looked at typical situations where you have a confined aquifer overlain, maybe underlain also, by a low permeability confining layer or an aquitard. So let's say we have an initial equilibrium head through the confining layer. Let's just say for simplicity it's linear. And then we apply a step drawdown in the aquifer that applies at the boundary between the confining layer and the aquitard. And if we look at how the head distribution in the confining layer will change in time, it will propagate, that drawdown in the aquifer will propagate slowly up through the confining layer until some future time where we'll again approach some new equilibrium with a new linear head distribution through the system. So we know how to describe that mathematically, again based on time and the hydraulic properties of the system. And if we plot that relationship up in a non-dimensional form, okay, we'll get this type of nonlinear curve relating dimensionless drawdown to a measure of dimensionless distance or dimensionless time, okay? And one of the things to note from this plot is that the volume of depletion would be directly proportional to the area under the curve. Okay, so if we want to estimate depletion, we need to do something with this nonlinear curve. But if we look at the area under the curve composed of this, let's say parts A and B, and then look at area C, what we see graphically is that this area C is pretty close to being equal to the area B. Not quite, but it's close. And maybe for an approximation, given all the other uncertainties in the system, let's just substitute this area C for this, and then what we wind up with is a nice unit rectangle of 1 by 1. And it's always much nicer to deal with a simple rectangular shape rather than some nonlinear curve. So maybe this is worth doing. So the analogy then is in, let's say for early time, this nonlinear curve, the area under this curve would be proportional to the volume of depletion. Let's replace that with this rectangular shape that reflects the drawdown in the aquifer at the boundary that will say propagates some distance into the aquifer, and then there's no drawdown above it. Okay? And we could call that distance a virtual distance of penetration, which again is based on the hydraulic properties. And then if we could estimate that distance, the volume of depletion is simply proportional to the distance, the drawdown, and the area over which it's effective, as well as, of course, the storage properties. So, and again, this is described in this paper that was published about 2 years ago. So then we wanted to test this just to demonstrate that the method works. So we set up a numerical experiment for a hypothetical system in which we could apply the method, but one in which we knew exactly the answer. So we set up a mod flow model of a 3-layer system where we have an unconfined aquifer overlaying a thick confining layer, overlying a confined aquifer, and we had about 25 wells distributed spatially in the confined aquifer, about 100 kilometers by about 50 kilometers, represent a pretty sizable area. Okay, and then we applied on the land surface some topography and said there was drainage through a network of rivers, and we had recharge over the system, and then and again, we applied some representative properties, and again, the values don't matter, but one thing I want to point out is of all those wells, we pumped cumulatively for 25 years in the model, there was total withdrawal of 4.1 cubic kilometers of water from that system. So if we look at the budget, the hydrologic budget for this groundwater system under steady state pre-development conditions, we have a budget again for 25 years in terms of cubic kilometers. And then after pumping for 25 years, we see the shift. What we've added then was, of course, wells, an outflow of about 4 cubic kilometers, and that's balanced by storage close to 3 cubic kilometers, an increase. There's nothing coming in from, no inflow from constant head boundaries under pre-development conditions, and there's almost 1 cubic kilometer cumulative under the development conditions. And there was actually a slight reduction in outflow to constant head conditions. So all 3 factors entered to varying degrees here. And of the depletion, what we had was about 2.9 cubic kilometers came out of the confined, low permeability confining layer, and just a very small amount came out of the aquifer. Okay? So now we have this ideal hypothetical system for which we'll assume that these are the truth. And then let's apply our method. We looked at, so again, the idea here is if we know a lot about the system, does our method of approximation work? Okay? And again, this is the average drawdown in the system over time, over the 25 years of pumpage. So applying our method, we look at where the representative kind of half of the drawdown applies, and that applied was applicable over a period of about 20 years. And we plug those numbers into the system, and what we wind up with is an estimate of depletion during the 25 years from the confining layer of 2.8 cubic kilometers. And that compared with the mod flow calculated confining layer depletion of 2.9 cubic kilometers. So we were pretty pleased with this comparison as a demonstration of the application of this approximation method. So now the next thing was to look at a real system. Okay, and so we looked at the, in South Dakota, we have the Dakota sandstone, which is a classic artesian aquifer system. Okay, and it's much more aerial extent, it underlies much greater area than South Dakota, but there were several studies in South Dakota that gave us some data. And in South Dakota in particular, the system was developed really starting in the late 1800s. And wells were drilled, and it was under great, well, artesian head. So anytime they drilled a well into the Dakota sandstone, they had a free-flowing well. Took no energy, no cost to produce water beyond that, the capital cost of drilling the well. Okay, so this was a wonderful boon to the agricultural economy and the municipalities in South Dakota. And this is a picture from one of Darton's studies in 1905. Okay, and that water column rose almost 100 feet. Okay, so we looked at the Dakota system from pre-development time to 1980. That's almost 100 years. And agglomerating multiple sources, we came up with an estimate of almost 20 cubic kilometers of discharge through wells during that time period. Okay, the drawdown in the system averaged something close to 50 meters, probably a little less than 50 meters. And what time is it that average applicable to is probably on the order of 50 years. We know something about the properties of the system based on studies by Chris Nuzell and others, so we actually have better estimates here than in many other systems with confining layers. So plugging our best estimates of the system in, we first computed what the depletion from the aquifer was, and it was something on the order of 0.4 of a cubic kilometer, which probably represent, well, we think is on the order of 2% of the total discharge through wells of this system. And if we look at the confining units, applying the method of approximation or estimation that Chris and I, Nuzell and I developed, the depletion from the confining layers is on the order of 15 cubic kilometers, or about 76% of the total withdrawals. And actually, I think it's probably more than that, but there's uncertainty in the estimate. If we look at it from another perspective, the leakage and depletion of the confining layers accounts for about 97% of the total change in storage in that system. The total depletion of that is, over that 100-year period, there's at least 15 cubic kilometers less water stored in South Dakota's groundwater system than 100 years ago. So let's shift a little bit from thinking locally and regionally to thinking more globally with issues of climate change and global warming and sea level rise. So if we look at, again, a world water budget, and this particular slide shows numbers both in terms of volumes and fluxes or rates of flow, okay? And thinking in terms of climate change and global warming, it's very well accepted that if we have significant melting of glaciers and ice caps, that water will ultimately wind up in the oceans and we will have sea level rise. That is, the reduction in the volume of ice will be balanced for the most part by increase in volume in the oceans. Okay? Well, for the very same reasons, if the volume of depletion or the reduction in volume of water stored on the continents in the subsurface is reduced substantially enough, that should be also balanced ultimately by an increase in volume of water in the oceans and in sea level rise. And the question is then, how much and what are the numbers showing? So in terms of doing these, we could think in terms of estimating groundwater depletion. Should we be looking at rates, as most of the global climate community is doing, or do we have to do it on a volumetric basis? And I would argue that we have almost no choice, although obviously there's an equivalence between the two, but the estimates for groundwater really have to be based on a volumetric approach. There is just too much uncertainty, too much unknown about recharge rates and discharge rates. We can't look at all the fluxes and come up with a balance looking at depletion as a remainder. Okay, we have to actually look directly at what the drawdowns are and estimate depletion volumetrically. But if we do it over long enough periods of time, we should have some success. And what I've done is try to get estimates for the 20th century, a 100-year period. And during this 100-year period, we have some, let's say we have a consensus, almost a consensus, on what global sea level rise is. And it's something on the order of 15 centimeters in 100 years. Well, what I did again is a very detailed aquifer by aquifer, basin by basin, region by region estimate using a combination of methods and just getting the best estimate as possible. There's a couple of places, particularly in the Northwest, where there's actually been a net increase in the volume of water stored in the subsurface over the last 100 years. Although in both of these, it's changing over time, and these are rapidly switching to a net depletion. But just looking at the 20th century, my estimate is that there's somewhere between 700 and 800 cubic kilometers of depletion of our groundwater resources in the nation. Okay, now that's a large number. That's a lot of water. And clearly the biggest one is the High Plains Aquifer. And again, this number differs from the one I showed you before because I'm only trying to come up through the year 2000 here. And there was actually that other number added 3 or 4 more years after that. So, which is another point, this number is increasing continuing to increase with time. So, well, what's the implication for sea level rise? Well, we have a rough estimate of the surface area of the oceans, okay, and that's a pretty big number. But if we take that volume of depletion and spread it out over the surface area of the ocean, we wind up with a rise of 0.2 or 0.2 of a centimeter. And that's a small number and is approximately equal to about 1.5% of the observed sea level rise. So what I would conclude is that groundwater depletion in the US, just in the US during the 20th century, is a small but non-trivial contributor to sea level rise. Clearly small, but it's there, and it's, I think, measurable, and it's a contributor. Then we could go on to what about the rest of the world? Well, again, we're still in the realm of speculation here, but maybe an educated speculation about the total 100-year global depletion. I would estimate, and this based on looking at where there are problems in the North China Plain, in India, in most of the Middle East, North Africa, Australia, Mexico, any place where there's land subsidence, 3 to 7 times greater than the depletion in the US. And you could note also that in the year 2000, we finally have some statistics on global groundwater withdrawals, and it's on the order of 7 to 8 times greater globally than in the US. So the 3 to 7 times, some people that I've spoken to from other countries say I'm underestimating it, but let's say it's in that realm, then the global groundwater depletion could contribute somewhere between 0.6 and 1.5 centimeters, which means we're talking somewhere between 4 and 9 or 10% of the observed sea level rise being caused by groundwater depletion. Okay, and so again, it's a small but definitely non-trivial contributor to sea level rise. And from that perspective alone, I think it's worth knowing about. And it's a factor that the global climate change community generally doesn't want to hear about. So we have an alternative theory for what contributes to sea level rise, and it's not this one. But there are some people thinking of alternative theories. So I mentioned earlier that maybe there's some other things related to global effects of groundwater depletion. And in addition to sea level rise, well, maybe it's contributing to changes in the chemical composition of the ocean, water, and so on. Well, we don't have time to talk about all these, but let's take just a really quick look at whether or not the change in mass distribution associated with this depletion might actually affect the Earth's rotation and the length of the day and other related factors. And there have been a couple of studies looking at this sort of thing, very large-scale global geophysical redistributions of mass and what their effect is. Well, Chow in 1994, at the time he worked for NOAA, I believe, he thought that groundwater might be a factor to consider. And if you look, maybe you can't see it, but if you look in detail at his compilation for groundwater under all these different factors, question mark, question mark, question mark, question mark. The numbers weren't there. There was no way to assess it. Okay, and so again, one of the things I'm trying to do is get some numbers here so that we could look at this. So global mass redistribution could affect the Earth's gravitational field, changes in the Earth's rotational speed, which in turn would affect the length of the day, and actually might contribute to rotational axis orientation or changes in polar motion. So one of the things we always look at in terms of rotation is a classic analogy to dancing ice skaters, okay? And we see this during the Olympics, and when they're dancing, they start out with their arms out, and they spin around, and they pull their arms in, and they go faster and faster. So the question is, if we're transferring a large mass of water from the continents at high elevation, the high plains is at an elevation of 3,000 to 4,000 feet above sea level. If we're moving large masses of water from the continents to the oceans, okay, can this shift from high elevations to sea levels follow the same analogy? So going from high elevation to low elevation, is that analogous to the ice skater pulling their arms in and spinning faster? So should this redistribution of groundwater cause the Earth to spin faster and the length of the day to decrease? So how many people think that this is an appropriate analogy and that is indeed what the effect would be? Anyone? Okay. Anyone who thinks it would be the opposite? Well, not too many people voting, but it's about a 50-50 split. So I don't know what that means, but my intuition told me that this is a valid analogy, and as we shifted water from high elevations to sea level, the Earth would spin, again, we're talking very small numbers here, would spin a little faster, and the length of the day would. Well, of course, I was wrong. Okay, because what you look at, the distribution of the oceans on the Earth, there's a much greater surface area at the low latitudes than at the high latitudes. So if you look at this picture of the globe, well, you see the elevation here is just trivial. You can't even see the change in elevation. But what happens, that water that winds up in the ocean is distributed over the entire surface area of the oceans, and the speed of rotation is a function of the angular momentum, which is your distance from the axis of rotation. So those of you who said it's the opposite effect were correct, okay? Because what happens is that most of the mass gets shifted further from the axis of rotation. And so the Earth will actually slow down a tiny bit, and the length of the day will actually increase. And we're talking about, Chow also did the analysis for surface water reservoirs, which have exactly the opposite effect. And he calculated for surface water reservoirs that storing water at higher elevations will cause the Earth to spin a little faster and reduce the length of the day by about 6/1000ths of a millisecond. Okay? And for groundwater, I would argue that, and the calculation is actually pretty complex, but for groundwater, the effect should be about the opposite, somewhere in that range also. So if you compare the surface water reservoirs with groundwater, as we look forward in time, one of the interesting questions, will the present trends stay the same? I would argue that for the next century, we're not going to be building dams and reservoirs at the rate we did in the last century, but we may be pumping groundwater at a continuing high rate. We've got to get the water from somewhere. So as we think about this, I would argue groundwater depletion, as I define the term, is not quite the same as groundwater mining, in that groundwater depletion itself is more generic and may or may not be recoverable in a short period of time. This all gets into the depletion, and the magnitude of it gets into issues of sustainability and groundwater management, water law economics, and all the related issues that are very difficult to deal with. In the High Plains Aquifer, we have this high magnitude of depletion. Springs have dried up, streams have dried up. Is this something that, if it was starting today, would it be allowed or should it be allowed? And that makes for an interesting question. Certainly, groundwater depletion on a local and regional scale can affect the sustainability and the viability of a water supply, both groundwater and surface water. And there are detrimental environmental effects, including effects on ecosystems and stream flow that maybe 50 years ago weren't quite as recognized, or the costs associated with that weren't as recognized. So in some cases, such as the High Plains, but other areas, the groundwater development is simply unsustainable over the long run, and water managers either have to think of some way to increase the supply or reduce the demand. Okay, and there are a number of ways to do that, but that's what the managers have to do. So we could ask in another sense, is groundwater depletion always bad? Should it be banned? And again, we could look at the High Plains as the best documented and most extreme case of groundwater depletion. And another way to look at it is the many decades of groundwater depletion have built up a multi-billion-dollar-a-year economy. It's contributed greatly to the wealth of the nation and particularly the wealth of the region. Okay, and so there's an issue. It's not a technical one entirely, of how do you trade off. Clearly, there have been enormous benefits to very, very many people in this region. Okay, and there have been some environmental prices to pay, and it was known really from early on that this was unsustainable. Okay, but yet there were enormous benefits. So should it have been banned or prevented, or is it always bad? Well, it's not such a simple question. So again, as we wrap this up, I would argue that groundwater depletion can indeed affect the world water budget, and we should be aware of that. The amount of groundwater depletion in the world is very poorly documented. Okay, and I would like to see that corrected, and I'm doing my bit, at least for the US part of that. Depletion from low permeability confining layers has been generally unrecognized, and people are not looking at it, and yet in many systems, such as the Dakota Sandstone, where you're pumping out of a confined aquifer, where's that water coming from? Most of the depletion is coming from, well, most of the production really is derived from leakage out of confining layers. Okay? And that leakage mostly represents depletion of water out of those low permeability confining layers. The assessment that I'm near completion on for the US, I really would like to see it integrated into a global assessment so that we can get the numbers and get a handle on it. So with that, thank you.
Appreciate it if you would wait for the mic to ask your question so we can record it on the videotape.
One in the back.
Hi there. I'm a solar energy advocate, and solar electric roof shingles and solar panels use no water in the production of clean, renewable electricity, and coal-fired, oil-fired, natural gas, and nuclear power plants use a minimum of 186 billion, that's with a B, gallons of water daily in the production of dirty greenhouse gas-producing electricity. So if California especially, who has an abundance of sunshine, wants to preserve its freshwater resources, we have to go solar because solar panels use no water. But that's not what I want to talk about. I want to talk about, first of all, Coca-Cola and companies like that. They're buying up, I hear these programs, they're buying up the groundwater from all these countries, third world countries, and they're just ruining all the farming in the area. And T. Boone Pickens, well, I think he's a thief myself, but they have this strange law in Texas where the government controls the surface water, but the groundwater is owned by the farmer. And so I think it was meant for the farmer so he could get groundwater, but T. Boone Pickens bought a piece of land above an aquifer and arranged it so that he can sink these huge pumps, and he's pumping out all the water. The local farmers are all going crazy. And what he does, then he bought the politicians to have a right-of-way straight to the cities, and he put in this pipeline, and now he's claiming to be environmental because he's using wind power to move the water out of the aquifers to supply the electricity and pump it into the cities. And he's basically a water thief. He tried to do that here in California. He goes under this environmental thing where he's using solar and wind, but he's really stealing all the groundwater. And he said on the show, it was the Commonwealth Club, that he's the largest owner of groundwater in America today. So this is kind of a thievery going on of what I call the commons, and it should be stopped immediately because these guys will just steal everybody's water and they'll ruin the system and leave us in, and then they're gone with the money and there's no more water. So this has to be really worked on. There has to be new laws written that groundwater is part of the commons, like the surface water, and not privately owned by crooks like T. Boone Pickens. Thank you very much.
Okay. I'm not sure there was a question there, but one of the problems we have in the US relates to water law. And one of the facts are that water law is primarily governed by state regulations and state laws. And every state has their own set of rules and laws. It makes it very difficult to bring in any kind of optimal management schemes or plans or policies at a national level. And this is kind of the situation, and there certainly would be many benefits of generating a more uniform code. But you're correct about Texas, that the groundwater is considered a private property. That, to a large extent, is kind of at one end of the spectrum. Most states in the US, it's really treated as a public property with rights given to use for beneficial use. But in Texas, it's a little different. Not too many states really consider it a true private property. And, I'm not sure that T. Boone's Pickens' plan to sell water to Dallas is actually in force yet. I know this was his plan, but I hadn't heard that it's actually operating yet. But you certainly have some very good, legitimate concerns about what's going on in Texas and in other areas. But it goes right back to what Mendenhall said in his 1909 water supply paper 100 years ago. The principles were there. If one, and this is the tragedy of the commons, in that it may be a private property associated with your land, but if you pump it, you're drawing in water from other people's property. And that's the hydraulics of it. You can't just pull your own water out. So in parts of Texas, they have underground water management districts that are supposed to deal with issues like this. And I don't know enough about it to know if they're successful or not. But again, over-pumping, exploitation, this is an issue. You raised the concern about bottled water. I don't think it's quite as serious. You look at the volumes of water that are being bottled compared with other uses of water, and it's really not that big. They're not drying, the companies like Nestle and Pepsi-Cola, Coca-Cola, whoever's got the big water bottles, they're not drying up the water resources of the third world. There may be some local issues and local problems, but in the US in particular, most of this is a perception problem that people don't want water from their local area to be exported, which is what they're doing. And in terms of the quantities, they somehow overlook all the water uses by farmers, municipalities, and industries that are pumping hundreds of times as much water as the bottling plants. So there's something about it that touches a nerve of people. But in terms of general use, I don't think it's that big a problem. In terms of the logic of paying $1 or $2 for a small bottle of water, I'd much rather drink the tap water. So, it's something that, is beyond just a technical consideration. So it's hard to explain. But there have been many, many protests and lawsuits in the US about bottled water plants. But in general, I don't think the magnitudes of the volumes are that serious. Certainly not compared with agricultural use in the US.
Okay, just as a comment on this, and I don't know anything about solar cells, but Dianne Feinstein objected to building solar cells in Mojave Desert, also on the grounds that they use groundwater there, I think, for cooling. But that's not part of my question. There was an idea floated about what is called as mega watersheds. Have you heard about this? This is something that Robert Bisson is pushing, and these are, to quote, tectonically derived watersheds that are conductive, and they are composed of fractured bedrock, and they transport water and they are replenished at significantly higher rates than traditional watersheds. I know nothing about this except what I just read on the website. Any comments on this?
No, I don't. I'm not familiar with that. I don't know, but so I don't know if they're talking about very, very deep groundwaters in tectonically active areas. Is this what they're talking about? Yeah, I don't know, but I would be kind of doubtful that the volumes of water moving through those very deep systems are anywhere near the volumes moving through the shallow aquifer systems. But again, getting back to one point that the earlier commenter made about water use for energy, that's something that is substantial that a lot of people don't recognize, that so many sources of energy involve a large magnitude of water use. And that's a very serious issue, and there are a lot of environmental impacts associated with that water use and the release of thermally enhanced waters. So.
I just wondered, does the USGS keep records of pollution of groundwater? And also, if you do, what about the sources of that pollution, whether they come from industrial or agriculture or whatever?
We have a lot of data on water quality from many perspectives, but we don't attribute contamination to sources. That's really in the purview of the Environmental Protection Agency. But all our water quality, not all, but most of our water quality data is available to the public over the internet. And so you could search and see what's there. But as far as attributing sources of contamination to that, that's generally not what we do. You know, except there's been a few research studies that we do where there's a known source, you know, but we don't get into remediation, we don't clean things up, we assess the resources.
Yeah, I guess in the first half of your presentation, we were talking about the drawdowns and subsidence. Some of those drawdowns, correct me if I'm wrong here, would be worse if it hadn't been for the subsidence, because the water level is dropping relative to some base datum, but in some cases the surface of the land is also dropping because of the water extraction, right? And so the depth to water situation would actually be worse if it hadn't been for that subsidence.
Yeah, but what you're talking about is a ratio on the order of 10,000 to 1. So if the water level drops...
Well, I mean,
So-
you had that, maybe that was an extreme case of the San Joaquin Valley where it was
That was
tens
an
of
extreme
feet
case,
of
yeah.
subsidence.
Yeah, no, that
Yeah.
was an extreme case.
Okay.
And not typical.
Okay.
In most areas, coastal plains of the Atlantic coastal plain around New Orleans, other areas there, the subsidence is on the order of millimeters to centimeters for tens of meters of drawdown.
What kind of fluctuations do you see in groundwater levels when you have an area, say like the size of Colorado or so, that experiences a small, like 5 to 7 year drought? And is it different in like developed areas versus non-developed areas?
I'm not sure I understand the question.
So if you have an area, we'll say like in California, right? We've been having a bit of a drought over the last however many years. I don't know. I just moved here, but do you see, like, say you have a decade of the regular rainfall, or like decades of regular rainfall, and then suddenly you have 5 to 10 years of what you would call a drought, much less rainfall.
Yeah.
Do you pretty quickly see a drop in groundwater levels, or how responsive is that?
It depends a lot on the local geology or the geologic framework or the hydrogeologic framework. The responses would generally be quicker and of greater magnitude in an unconfined aquifer. The magnitude would probably be greater in a fractured rock unconfined aquifer than in an unconsolidated sand and gravel. In some fractured carbonate aquifers in the Northeast, there was a drought in the 1960s that went on for at least 5 years. And there were long-term records in some of the carbonate systems of water table declines due to the drought of several tens of feet. Okay, and in other areas where you're close to a major river, which acts as a nice boundary condition and control on the system, you might see a decline on the order of a few inches in response to the same drought. So the answer is it depends. But in the deep artesian systems, you'd see very, very small responses to the drought because they're pretty well buffered.
Hi. In your map that shows the intrastate depletion for the Ogallala aquifer, there's an area like in western Texas that shows depletion, but then southeast of there's an area of replenishment. That it was blue, an area that seemed to be replenished, that was blue. Do you know the basis for that replenishment there?
Let's see if we could get to that. because it's one of the first slides. Okay, and down there. Basically, I'm not sure. No, sorry. I'm looking at that and I don't. Because it's interesting that it's, we're talking about, it's probably small. You were probably talking 10 to 20 feet, something in that order. That particular, I'm just not sure. I know what's going on in Nebraska, but I'm not sure what's going on there because it's not that far from the areas where you have, T. Boone Pickens is up in this area. In Nebraska, it's mostly water diverted out of the North Platte and South Platte rivers. And so they have a network of canals that diverts the water to irrigate farmland. Okay, so they're basically importing water onto areas that, they're basically increasing the recharge by irrigating with a flood irrigation type in some of the areas, sprinkler irrigation in some other areas. But by applying all this water, they're increasing the recharge to the water table many-fold over what is natural. And that increased recharge then, due to excess irrigation water being applied, causes the water table to rise.
That was actually, it's a perfect segue into my question. So early on, you had a slide in Nevada, Las Vegas area, and you mentioned that there were reasons why the water levels were stabilizing. I'm wondering, with respect to all this, the depletion, what is the implication with respect to recharge, particularly recharge rates, maybe with respect to average recharge rates that we usually talk about in models versus something more extreme like an El Nino event? And were some of these stabilizing events recharge events, or was it different management of the wells, pumping?
When you look at most of these areas, when you see a long-term trend of a decline like this, maybe some of this is El Nino events in wet years, but the effect really comes during the wetter years is that the farmers don't pump as much. Okay, and that's the direct cause, much less related to an increase in recharge, because particularly in most of these arid areas, you're talking about recharge maybe changing from 1 or 2 millimeters a year to 10 millimeters per year. And in the big picture, that is pretty insignificant. So it's really the pumpage, and most of the pumpage is agricultural. Certainly in Arizona it is, and you see similar recoveries throughout much of the Southwest, particularly in Arizona, and it's really, the effects are dominated by the pumpage. And when you have anything causing a change in pumpage in the Phoenix area, south of Phoenix, so much of the agricultural land has been displaced by housing developments. It's been suburbanized. And that, coupled with the importing of water from the CAP project, the Central Arizona Project, Colorado River water, there's been a great reduction in the volume of water being pumped from wells. In Las Vegas area and in parts of southern Arizona, that's also coupled with the implementation of some artificial recharge projects. So that's where the increase in recharge comes from the water managers who take excess water, usually imported water, at times they have some excess, and apply it in pits and ponds and let it recharge. So there are a couple of things going on.
Yeah. Okay, next. At the beginning of the talk, this is the most serious problem facing us today. And then depletion, is that, you mean it's gone forever? And then later on in the program, you had a slide with some terrain, and it shows it goes back into the ocean. Is it gone forever? Does it go back to the ocean? Or what is it?
Well, I mean, we certainly believe in conservation of mass. So if you remove it from the subsurface, it's got to go somewhere. And it's all part of the hydrologic cycle. In terms of a specific aquifer system, the depletion out of the High Plains aquifer is only recoverable over a period of centuries, okay, many centuries. The recharge rates are just too low. And the same is true in most of the southwestern US. But if you go to the eastern U.S. on the Atlantic coastal plain or the Gulf coastal plain, Arkansas is really one of the major groundwater users in the country. They're using groundwater to irrigate and grow rice, which you could debate about the logic of doing that, but that's what's being done. And there's a lot of drawdown and a lot of depletion, but it would be recoverable over a much shorter time frame if they stop pumping.
So depletion doesn't mean gone forever.
It does not, depletion by itself does not mean gone forever. The term groundwater mining, and then there's a bunch of terms that are used, but groundwater mining is another common term which has more of an implication of being non-recoverable. And by non-recoverable, you're generally talking over, the time frame, a human scale time frame. Okay, but even the water levels in if you give it enough time, thousands of years, it's recoverable. But groundwater mining generally refers to something that's not just the word mining. You're removing it and you can't put it back. So, yeah.
I've got a question.
Yeah. Okay. Yeah.
I don't have much of a science background. I'm here to get some of that education on these issues, but I'm curious about the human impacts of some of this groundwater reduction and water scarcity. You talked about a few regions in the world where there's a tremendous amount of depletion, and of those regions, I think you mentioned part of a basin in China, North Africa, Middle East. Do you see there being future flashpoints and conflict between two countries or within a country as a result of all this depletion?
There's certainly a conflicts. There's a term that's popular in the last few years called transboundary aquifers. And these are groundwater systems that are logical hydrogeologic units in the subsurface that cross some type of geographic boundary. In the US, it might be from one state to another, but it might be US-Mexico, or in the Middle East, it might be Jordan and Israel. Okay, and then you have enormous political problems. But whether anyone would go to war over water rights is debatable, and it's kind of a popular notion that there have been and will be fighting over water. Okay, and yet there's very few documented cases. Interestingly, all the problems in the Middle East centered on Israel and its neighbors, including Palestine. The one issue where there has been some cooperation and talking and settlement is on water. That's not what's causing the fighting there. And in fact, it's the one element that's pushing them to talk and collaborate, communicate, and cooperate. And but certainly it's an issue throughout the world. There are many cases and examples of transboundary conflicts, but very few, generally solutions are worked out. In the US, it sometimes requires going to the Supreme Court, but solutions are worked out.
On Mars, they're looking for groundwater right now. Do you think that the Earth would go through a groundwater scenario like that, with the pollution we're doing, the destruction of the environment, the diminishment of the snow caps on the mountains, the melting of the polar caps? Are we heading into some sort of Mars-like scenario here that people will be landing on our planet in years future, scratching the surface and trying to figure out what happened? Do you think that Mars, they cleared their forests, they clear-cut their forests, which were the anchors that held the sky down? Is that why Mars ended up the way it did?
I don't think so. I see many problems in the future on Earth, but that's not one of them. I think we can have some, if you look over geologic history, we've had some great extremes in terms of climate and conditions, and you just have to go back a few tens of thousands of years out of a history of several billion years to get us back to an ice age. Okay, and the ice age wasn't particularly hospitable to humans, but there it was natural. Okay, now we seem to be headed towards a global warming situation, which will have some serious consequences, and costs. But it's not, one way or another, we will survive that. Even if sea level rises, 100 feet, 200 feet, there'll be enormous displacements and enormous costs, but it's not going to wipe out civilization.
In your talk, you had mentioned that in confined aquifers, the confining layer could supply a, sort of an unexpectedly large amount of the water that's being pumped out of the aquifer. And do you feel that that may propagate up and may result in different sort of differences in the water above that, what's ultimately going into the aquifer, what you're seeing in unconfined layers that may be higher up, that kind of thing?
Okay, I'm not sure
So you've got a confined aquifer, right?
Yeah.
I think in the talk you're suggesting, right, providing a fair amount of water. So do you see that change, which is to say more water ultimately soaking into the confining layer? And you see greater, changes in what may be water table above or that kind of thing?
Well, the confining layers in general are confining layers because they have very low permeability, okay? And that means things propagate very slowly through it. And so the counterpoint is that they will eventually propagate through it. And so there will be effects, but again, because it's such low permeability, if there's an unconfined aquifer above it, the effects will be very slow and probably barely noticeable, and the rate of change in flux into the confining layer from leakage out of the unconfined system will probably be extremely small relative to fluctuations in recharge at the surface. So, but, yeah, those things are coming. That's one of the things about the confining layers. And also related water quality issues. I mean, we've got, in general, in groundwater systems, very slow travel times. And so some of the contamination problems that we've created over the years are still going to continue to haunt us for generations to come.
More leaky systems, say, where rather than a tabular confining layer, you have more pods of finer grained material, where you'd actually, essentially, I would argue, have more surface area of the tighter material in contact with the more conductive material. Might you expect to see more water produced from the finer layers?
Well, yeah, I think, yeah, and what you see certainly in some of the alluvial basins in Arizona, where you have intercalated lenses of clay, silty material, is the drainage out of those but low permeability materials is really what's contributing to the land subsidence. And in effect, that's telling us that these things are draining, and that's what's supplying a lot of the water, ultimately supplying water to the wells. So yeah, increase the surface area over which you apply a change in stress, and yeah, you're going to get more leakage out of it.
I just want to comment and mention that in our backyard here in South Bay, in the Silicon Valley, we have an extraordinary groundwater basin where imported groundwater, recharge of groundwater, groundwater pumpage, land subsidence, all rolled into one, are very, very carefully fine-tuned. In some years, when they get water from the aqueducts in greater demand, they recharge it. Sometimes when the drought comes, they increase the pumpage. If they increase the pumpage, the land begins to subside. So Santa Clara Valley is one example where, in fact, before 1930s, there was very large declines in water level. Then they started importing water and managing the groundwater. Now the water levels have come up. And so now this very carefully managed. In fact, in the San Jose area, I hear some of the wells have started flowing back again. So it is a very remarkable system where they finally figured out the connection between the surface water, recharge, and groundwater. So this is one of the best managed. In fact, I tell people in India sometimes when I go that they all know about Silicon Valley. But there is a water history of Silicon Valley where India can learn from, but India has still not waken up to it.
Generally,
and one other example, I was told by Bill Alley or somebody that there is some aquifer in Southern California where the imported water from Northern California has completely displaced the existing water. The old water that pretty much has been flushed out. And now whatever water is there, all recent water imported from elsewhere. It's very interesting.
Yeah. You look at some systems around the world, such as the Nubian aquifer in North Africa, and there the recharge is essentially zero. You've got a high volume of fairly deep, mostly confined water, extremely good quality, but a large volume that is on the order of 10,000 years old and older. And particularly in Egypt and probably more so in Libya, they've started major development of this water resource. And they're doing it with the knowledge that it's groundwater mining at its most extreme. Okay, they are truly have a non-renewable resource, and they decided that the economic value of developing it at some rate that they've decided outweighs the preservation of the water in the ground. So, they've made a conscious decision, generally, not universally, but generally with the knowledge that this is a mining operation.
Okay, I think it's past 7. I think we have had a very mature discussion. And I would like to thank
Thank you.